We're going to take a look at DC circuits, and in particular, what happens when we add resistance, take resistance out, and what happens when we have more complex circuits where we have multiple EMFs and not just a single one. So we'll start off by taking a look at what we call terminal voltage, and we'll hold off a little bit on RC circuits. Terminal voltage refers to what we get at the terminals of a battery. So if we can consider what's happening on the inside, there's always some inefficiency that comes from the fact that we just have physical material that charges need to flow through. And so we can identify those sort of in summation as resistance, as an internal resistance. That's why it's little r instead of a capital R. And then the fancy E is what we call an electromotive force. And in the case of a battery, this is promised to us by electrochemistry, whatever the two metals are that are involved. So the terminal voltage is what we see when we actually hook this up into a circuit. And one of the places where we use batteries the most is starting our cars. So we notice the effect of this internal resistance that when we engage the starter motor of our cars, that we're asking this battery to produce a tremendous amount of current. After that, after the car starts, then we don't even actually need the battery anymore, because most internal combustion engines come along with a small generator or alternator. There's a tutorial about terminal voltage that you can check out in terms of the context of problem solving. So now different kinds of circuits in series and parallel. A series circuit is one in which there's just a single path, and charges that are flowing through this path will go through each element sequentially. Now, this doesn't mean that it takes a little bit for sort of the current to fill up in the wire. All components of the circuit already have conduction electrons ready to go. So once the EMF is connected, all the charges start to move sort of in unison. So the total voltage drop is equal to the sum of the voltage drops across each individual resistance, but they all are guaranteed to have the same current because it's the same wire. And that means that we can take those three resistances and replace them with an equivalent resistance that's found by simply adding them. So the more elements that you add in series, the more the resistance increases. But in parallel, there are multiple pathways. But the one thing that's the same is that the voltage drop across each one is going to be the same. So the currents are going to add up to the source current. And then we can use Ohm's law to substitute, and we can see that the voltage drops are all the same. So they cancel. So to find the equivalent resistance, we add the reciprocals, and then the most important last step is to take the reciprocal of those. Sometimes that's a part that people leave out. And then the net result is that the more that you add in parallel, the less the equivalent resistance is. And that makes sense because it's multiple pathways. So there are several analogies. If you go back and look at chapter 18, I have a tutorial on different ways to visualize current. But the most important thing for you to do is to separate the difference between voltage and current. In Kirchoff's rules, we have more complex circuits, and it's not as simple as just series and parallel. So we have to do a little bit of thinking about that. And there'll be a tutorial posted about applying Kirchoff's rules. So we start off with the first rule, which is the junction rule. And this is kind of like a traffic light, really. If we think about A as being an intersection between three roads, the current that comes in is equal to the current that leaves, or the number of cars that come into the junction is equal to the number of cars that leave. And so this gives us a way of equating currents to each other. And that's going to give us an equation. In the loop rule, we take a walk around any given loop, and we know that energy conservation has to apply. So we start off with 12 units of energy per charge. We lose some here between A and B. We lose the rest between B and C. So this allows us to track the energy changes going around the loop and set those equal to 0. That's another way of generating an equation between the different variables that we're trying to track. So what we want to do is we want to try and identify current, and you're going to make a guess at which direction current flows. And sometimes your guesses are going to be wrong, and you'll know they're wrong because you'll get a negative current value. It doesn't mean that your efforts were incorrect. It just means that your initial assumptions were off. Now, sometimes we have multiple EMFs. If they're in the same direction, like for instance, going from A to B is a gain in energy and going from B to C is a gain in energy, then they simply add. But sometimes they're going to oppose each other. And this is what happens when we're trying to charge a battery. And of course, all of you have an experience of charging a battery every single day. So in order to charge a battery, we need a slightly bigger EMF than the EMF of our battery. So in the case of your cell phone, the battery in your cell phone is 3.3 volts, and we charge it with a USB cable, which is 5 volts. And here's a car battery being charged by the alternator. The alternator, if you have a car that gives you a gauge readout on the alternator, should be at least 15 volts in order to keep charging your lead acid battery. So if we have EMFs in parallel, this really only is going to work if the EMFs are the same. And then in the rest of this, we're going to leave off our conversation about capacitors. Because we already talked about it earlier in chapter 18.